Greetings everybody, we're back again for Bayes, and this is going to be our last lecture. I apologize in advance because I'm going to kind of steamroll this lecture. I'm going to go through it really quickly. Typically this might take me 2 or 3 lectures if I'm going to go through all the details, so I kind of want to just tell you about something. Those of you that have taken a grad level inference class will already understand some of the techniques that we're doing. Namely the method of moments technique. I'm going to show you this technique and use this technique in the middle of Bayesian analysis, and that's going to be kind of interesting. If you're unfamiliar with what that method is, take Stat 5114 next semester and I'll tell you all about it. So that's grad inference. The level of that class is a little bit harder than probably the level of this class, just because we're dicing up so many different inferential techniques, where this is all Bayes. But Empirical Base is a neat technique that it kind of makes a non-Bayesian twist in the middle of the analysis. So I'm just going to get underway. One more announcement. We will be doing the review session tomorrow at 5:30, usual time. If you have any logistical questions, probably just hold off until then and you can ask me. Put questions on Slack. I'll look at them before we come in, spend a couple hours catching up with you guys. Friday is our final exam spot. It's at some ungodly hour, like 7:45 in the morning. What I'm going to do is I'm going to send out 5 questions or so to you. I had said that it would be a 24-hour exam. I'm going to give you 72 hours. So around 10 o'clock in the morning on Friday, I'll send out the exam. And I would like all your materials by Monday at 10. So we went from a 24-hour exam to a 48-hour to now 72. It'll give you guys a little bit more time in the weekend to put everything together. You'll be sending your materials over to Sierra, and I'll get a hold of them. We'll get you all graded up. If there's any serious concerns about something, just send me an email directly, and I can answer it. For instance, somebody asked me, they were worried about their grade in the class, and they said that they had about a 75 on midterm, and thought that that wasn't a very good performance and was unsure where they are. If you do go back through the lectures, you'll notice that I drew a histogram of the midterm scores, and I told you what the grades were. So if you want to review that, you can, but a 75 on the midterm I consider an A. And so even though there were people right around 100 on this midterm, that was about the average. And I think that was okay. It actually was a bit higher than the average, wasn't it? I think our average was a couple points down from a typical average. So it's trying times, difficult, so I'll give you a little bit of mercy. If you were really far down on the midterm, you can always turn in the midterm as well. So nothing is too late. I would have liked it a lot sooner, but getting everything in by Monday, we can consider it and look at it. You're going to send the finals to Sierra and me, and so we'll both be taking them. So if you mess that up, it's okay. So pick, choose, and we'll have everything together. But the materials, extra credit stuff, send to Sierra directly, and we'll go through it all. Look at your effort, look at your analyses, notice that you learned lots of things, and that's what this class is really about. So without further ado, let me tell you about one more topic. There's full books written on this, but it's pretty simple technique. It's called Empirical Base. And so the empirical part has something to do with using data to calibrate your hyperparameters. So throughout this class, I've kind of said you can't put data into your priors. So, and we talk about a number of reasons why. If you do use data in your priors, you have to be really careful. And this is a technique that allows for you putting data in your priors. So now your priors have data in it that also your likelihood has. So this is a gross violation of the likelihood principle, if you're into that sort of thing. That used to perturb me a lot. But through an example I'll show you in a minute, this can be a good idea. So you have to be careful when you employ this technique. I think about it a lot still to this day, and there's certain instances where I will use it, and there's certain instances where I won't touch it. You'll notice that in the Bayes lasso paper, they have an empirical Bayesian method for the regularization parameter in lasso. Remember that regularization parameter is in the prior, so it's using a Laplace prior, and they're using data somehow to estimate that. It's an empirical Bayesian technique. Okay, so let me just give you the basic set of what empirical Bayes is. There's one common step, and then there's a bunch of choices that you can make, and I'll show you a couple choices, or I'll show you at least one choice, and I'll allude to another one. But here's the basic Bayes setup in general. I've got my data coming in, and then I've got my prior. So here's my prior. So I have my generating function of the data, which helps me to build the likelihood function. So if I knew this parametric thing, I could build the likelihood. And then I pick a prior. And I want to be a little bit more specific in my notation. I haven't been using this notation very regularly in class. I think after the first couple weeks, I stopped writing in the conditioning on the hyperparameters. But this is to indicate the hyperparameters of everything. So this is going to be some parametric distribution on theta, my prior, and I have to tune that prior. And the question is how do you pick those hyperparameters? And we've had a number of different answers to this question. Maybe we take a limit and we end up getting something like a Jeffreys prior. That maybe the Jeffreys prior, if you use the Jeffreys formulation, it picks your hyperparameters for you. It also picks the distribution that's conjugate, and if you're in an uncompact space, i.e. like an infinite space, that's going to be an improper distribution. So it takes the limit of these things. So we've talked about a number of different ways of picking hyperparameters. If you're a scientist and you know something about your analysis already, maybe through some other data, you could pick these hyperparameters to match what previous inferences have done. That's called a subjective analysis. Jeffreys, something like that, is maybe more akin to an objective analysis, but just keep in mind what the objectivity criterion is in that. It's something about transformation invariance. In one dimension, that's a reference prior, and it ends up having some distance function between the posterior and the prior, and reference prior is such that the posterior pulls away from the prior as fast as possible with respect to a Kullback-Lagler divergence metric. We did not go through that in class. But my point is that you choose the criterion. And so every objective analysis is also subjective because you have to pick what the objectivity is. So what it is you're guaranteeing in the analysis. If you ever say something like, well, I want to guarantee everything simultaneously, good luck. So that's not going to happen for you. Not in anything other than maybe one dimension. In one dimension, you can have a lot of properties simultaneously. So that's a lot of words about different ways to select hyperparameters, but empirical Bayes has a different way of doing it. And so there will be data in here that calibrates these things. So again, a violation of the likelihood principle. So if you've taken inference, you've at least experienced what that is. But a Bayesian does this. So they just multiply the likelihood times the prior. And they normalize it. So we've got our proportionality symbol. My notation right here is that cap X is the collection of all the data. And I could write down the distribution for cap X. So usually you might pick a sufficient statistic or something like that and build that distribution. Any way you do it, we're going to get our posterior. So this might be our joint distribution of the data, which would be proportional to the likelihood function. If this was IID, I would just take all my fx, xi's, given theta, and I would plug them in. If everything wasn't IID, I could build this distribution anyway, joint distribution of all of the data. And so that's what a Bayesian does, is they build this posterior distribution. we have circumvented up until this step, selecting the hyperparameters. So I can write this down as an expression maybe, but it's not an analysis until I plug something in here. And so empirical Bayes always follows this first step. And then there's some choices. And so what they do is they marginalize. So just marginalize where I'm going to marginalize over theta. So here's my prior. This is my sampling distribution. I'm thinking about it that way. If you like to think about it as a likelihood function, that's fine. You're at no disadvantage. I'm just saying that this is normalized over x. But of course, I'm going to be touching theta right here. I'm upgrading it to a random variable, and I'm just marginalizing out. And so all empirical Bayesians, at least to my knowledge, build this marginal distribution. So they integrate over theta. And so keep in mind, by doing that, we've taken into account the parametric family that the prior lives in, what its shape looks like in general. And so I would say this has something to do with the prior distribution, at least the parametric choice here, but it doesn't have any thetas in it because we've averaged it. So this is in some sense like the, well, not in some sense, it's the average where we've averaged over theta. So it's a weighted average of the joint distribution. But by averaging over our prior distribution, we also have the hyperparameters in here. So here's my hyperparameters. The question is what do we do with this distribution? And there's many choices. So one such choice you might do, here's an empirical Bayesian method, is you might look at your marginal distribution, plug in all of your data, so plug in actual data, and then maybe you might maximize this function, argmax, over psi, and this would be psi hat, right here. And so what I want you to notice is what we really did is we're taking something akin to the MLE. So this looks a lot like the maximum likelihood estimator, but it's not a likelihood function that we're playing around with right here. It's the marginal distribution. But this is kind of akin to an MLE. And so what you would do at this point is you would go back to this distribution, right here, your posterior, and I would plug in this parameter. So my posterior distribution would be this, pi theta, given my data, and then I'm going to condition on this creature that I just found. And I'm just going to write down MLE right here, even though I recognize this isn't a likelihood function. But we ended up using the maximum likelihood procedure for this to come up with that. That's not Bayesian. So to do that. So a Bayesian analysis might be, well, let's just put a prior distribution on psi, but whatever that prior distribution is on psi, it's going to have hyperparameters. So we're going to have to do something with those, and we're just hiding everything under the rug if we do a fully Bayesian analysis. So you can pick this based off of objectivity criterions, subjective criterions, if you have knowledge about what theta might be. But empirical Bayes ends up plugging in a choice that maybe somebody that was non-Bayesian would make. And so this is a hybrid technique. So it was Bayesian in its setup. We get a posterior, but how did we pick the hyperparameters? Maybe we maximized. There's another way of doing it. So this is one choice. There's other choices. So I'll just say or choose psi hat using some other non-Bayesian method. So, just a reminder, step one is create the marginal distribution, marginalize over theta. We will build a posterior eventually, but let's marginalize it out and then use some sort of, I'll say, classical technique. So maybe I mean classical. Old technique. Here's one such way of doing it, maximize it. Here's another technique, another way of doing it, and I'll show you an example with this. If you're unfamiliar with method of moments, feel free to take inference and I'll tell you all about it. It can be a good technique. It can be a sloppy technique as well. Not my favorite in the world, but sometimes it works. So, or maybe method of moments. So, idea of method of moments is you figure out whatever the expected quantity is for x given theta, and then you match this thing to something like this, the first moment divided by n. So this is the empirical moment. And this is the theoretical moment. Yeah. Given psi. So here's your empirical moment. Now, if psi was two-dimensional, I haven't been very specific about this, then we would have to match two moments. So we might match this one and maybe the second moment. And I'm going to match this to xi squared over n. Basically, you come up with a system of equations and you solve that system.
You just wrote empirical moment twice.
Oh, I was wondering. This is not the empirical moment, this is the theoretical moment. So you work a calculus problem, you figure out what the expectation is. This is going to be some function of psi. This will be some function of psi as well. And then I match this to that and I solve for whatever psi is. Okay, there's an infinite number of ways that you can do method of moments. I'm going to show you one such way, and I'm going to use some choices that I read in a paper. I'll send this paper online, so I'll post this later this afternoon if you want to read through all of the details of this analysis. I'm not going to quiz you on this, I'm not going to test you on this, I'm just telling you something for the sake of closure in this class. And basically I want to highlight a very important result in statistics. So let me give you a real example. We've got two steps. Step one, marginalize, and then use that marginal distribution and do something maybe more classical to come up with some estimate of psi. So here's my example. This is very simple. I'm going to have xi's coming from a normal distribution. This analysis is a little bit funny. I'm going to have for each xi its own mean right here. And I'm going to let sigma squared be known. So you could estimate theta I, and I'm letting that be one-dimensional, and that's one-dimensional, using just one x. My analysis is going to be very, very similar to if I ended up having more of these. So if I had, no, not that. If I ended up letting this be replicated, where j goes from 1 to n, this is really the same problem. So, of course, in reality, I would like to have more data, but in terms of the analysis, in a comparison, it's good enough to use just one data point. We've talked about that before. So in our interval testing analysis that we studied, and we looked at the incoherence of p-values for the interval analysis, it was good enough to just look at what happened with one data point. If I had more data points, what I would do is I would average them together, and I would be using x bar. But if n is equal to 1, then x bar is just the xi. So for each data point, it comes from a distribution, and I could let all of these variances be different and it wouldn't change the result I'm about to show you. I just need the variances to be known. And so again, this is a simplified analysis so that we don't have to think about too many other things that don't actually impact the result. So first question, what's the MLE for theta I? And it's the mean. So the answer is theta I hat in the MLE sense is equal to xi. And if I had more data points right here, so if I let this be j goes from 1 to n, the answer would change to x bar. So I'd have xi, j goes from 1 to n over n, and this would be x bar I, and that would be our MLE. So if you want to study this with more data points, you're just going to substitute my x's for x bar. Not necessary to do for the example that I'm playing around with. So we'll just make it simple because it illustrates the point. Okay, so the answer is xi, and you might think if these were all IID, and in my example, these are all IID, you might think to yourself that you cannot get a better answer. And that's not true. We have to define what a better answer actually is. So let me give some context to this problem. Imagine theta 1, let's imagine maybe I've got 4 different thetas. So if p were equal to 4, that's what I consider the dimensionality of the problem. Let's consider some stuff that's unrelated to each other and they're clearly independent. So maybe the hay prices in Blacksburg might be theta 1. So just as an example, theta 1 is going to be equal to hay prices in Blacksburg. I have no idea how much hay costs in Blacksburg, but I'm sure that it's something we could figure out. Go out, collect some data, do some averages, and figure it out. So we go get data. So theta 2, let's say this is the number of cars exported from Japan to South Africa. I'm certain Japan exports cars to South Africa. I think I've seen Toyotas there, for instance. Hondas are there. These probably don't have a lot to do with each other. So this is a number of cars, not the price of cars, and this is the actual price of something. Let me change this to a 3-dimensional analysis because this will serve my point. Let this be the amount of gamma radiation found in Chernobyl. So in Chernobyl. I'm not sure if I spelled that right. So apologies to anybody from Chernobyl if I didn't spell it right. My point is that these things are seemingly unrelated to each other. And you probably wouldn't want to use x2 to infer what theta 1 was. So I probably wouldn't want to look at the amount of gamma radiation in Chernobyl to try to estimate hay prices. And you would say, look, the best answer you can give me is just your one data point for each one of these scenarios. And I'm going to show you something that's kind of weird, that you can get a better answer. So I can combine the data in a funny way, and I can get a better answer. What I mean by a better answer is the co-estimation of everything simultaneously. So if I wanted to just compute the error for each one of these things, and I think about those errors differently, you can't really get a better answer than this. So I would report this answer. But if I thought about my overall error, I have to report a whole bunch of stuff, and I'm going to be scored simultaneously on making all these predictions at the same time, then you can get a better answer. So let me give you something that's a little bit more tangible. Imagine you're looking at cell towers, and you're looking at their failure rates. So cell phone towers are responsible for us being in communication with the whole world. Let's imagine that cell phone towers fail independently of each other. And I want to regulate the whole system. Now we kind of know that the cell towers need to work in conjunction with each other, so it's a network that you're playing around with. But the failure of each cell tower happens independently of each other. So that's a system where I would score myself on the entirety of how the whole network is working, not just on the individual. And so that would be a better example. I think that's one of the examples that you look at on Wikipedia. So this problem has a name of using different data from unrelated sources to bring down the overall error rate. This is called the James-Stein Paradox. And I'm going to tell you about it. So it was back in the 60s, James and Stein had made this discovery. And a lot of people thought that it was incorrect. It couldn't be correct. That if you had independent sources governed by means that have nothing to do with each other, you probably couldn't improve on this answer. But in the global sense, it turns out you can. So people thought I was wrong. It turns out it's true, and we can demonstrate this for you. And I will demonstrate this for you, and I'll show you some graphics. But after a while, about 10 years later, people said, okay, it's right, this result. Question is what do we actually do with it? Is it meaningful? And it turns out it's used all over the place. Sometimes it can lead to bad answers, and sometimes it can lead to really great answers. So I'll try to make my point in the next couple minutes. So let's try to improve on this answer. It turns out if P is greater than 3, this answer is inadmissible. It means that the overall risk is too high. It can be beaten by some other estimator. So if you've taken inference, this is inadmissible. I didn't have time to teach us all the vocabulary of decision theory, but for those of you that know what that means, it means that there's some other estimator that exists that is going to be able to bring down the expected losses. So however you're scoring yourself on getting this answer right, there's something else out there that beats this answer everywhere. If P is 2 or 1, this answer is admissible. So if P is greater than 3, and 3 is the breaking point here, this answer is inadmissible. Now, it's kind of a funny thing that happens. And so people thought this couldn't be true. This isn't actually a paradox. This is just a misunderstanding. But there are wild applications to this. The cell phone tower example is probably a good one. I've also seen this being used in terms of evaluating overall hospital care rates. And so if I'm trying to understand what's happening at an individual hospital, this is probably a good answer. If I'm trying to think about what's happening in a network of hospitals, and maybe that's what I'm concerned about as a governor, there is a better answer out here. And so let's see if we can understand this. So as a Bayesian, our first step, and I called it the 0th step, is to choose a prior. So let me get rid of my silly example here. My example is just constructed to illustrate that I've got stuff with nothing to do with each other. It's independently generated, and we have different means for each data point. I'm going to coalesce this data and use it all together to estimate each one of these thetas in a second. So this is a very, very key step right here. Is this prior? It looks simple. It looks like the conjugate prior. It is conjugate. But our prior is going to anchor each one of the theta i's. And again, I goes from 1 to p. And they're going to anchor this at a common parameter. So I'm centering these all at the same thing. So I've induced some sort of dependence in my analysis by doing this. So common to each theta I. Okay. So basically, my prior for each one of the theta i's is this distribution centered at mu and common tau squared. This is the important part. And what we're doing is we're shrinking our estimates. So I'm pushing everything towards mu. Now you might say, you don't want to push too hard towards mu. If you have a whole bunch of data, it probably isn't going to matter how you pick this, but you're going to need enough data to overcome everything. So we need to be careful on how we select these parameters. But what we're doing is we're shrinking the analysis towards something. So I'm pressing all the thetas in a common direction. And so even though the xi's are independent of each other, and the theta i's had nothing to do with each other in the original problem, now they have something to do with each other through our prior. So some people will call this the shrinkage prior. I've been using the word regularization. So we're regularizing the space. And it's the same word that I was using when we were playing around with model selection, where we're pushing everything towards 0, a common parameter. So I'm pushing all the theta I estimates towards a common mu. This is the thing that gives, this is the wonderland, I would say, that we're trying to deal with all of the errors and estimating all of these theta i's simultaneously. And I'm not going to score myself on how well I estimate each theta I. Instead, I'm going to score myself in terms of how well I estimate all of them. So let me tell you what I'm going to use to measure how well I'm doing. I'm going to use something like MSE. So let me make a note. I'm going to erase some of this. Sierra, there's a question that popped up.
Yes.
What does it say?
Isn't this similar to the random effects distribution?
Yes. So looks and feels just like that. So question was, isn't this similar to a random effects sort of thing? Yes, the same hierarchical form, but my interpretations are wildly different here. So while the mathematics is going to work out just like playing around with a random effect, and it looks like this is a random effect, this is not a random effect, this is a prior distribution. So random effects are induced for a modeling purpose. So, but same mechanics, same mathematics. Hopefully that helps, but yeah, there's some similarity here. So I keep saying that I want to score myself jointly. And so some people will know what my loss function is if you know about decision theory instantaneously when I do this. So I'm going to score our performance using MSE. So that's just mean squared error. That's when the markers start drying up on me. So I'll do something like this. I'll look at I goes from 1 to P, divide by P, so I'm just looking at on average how well I'm doing, and I'm going to take my truth, theta I, and I'm going to compare it to my estimate, theta I. So if I were using the MSE, oh, and I'm going to square that out. So that's the mean squared error. If you want to take a square root over the top of this, you can. So and put it on the same scale as everything. But basically, I can use this as a scoring function to evaluate how well my estimators are performing. So we will look at this answer. What's the MLE? And we're going to compare it to the answer that I can induce using empirical Bayes. So far, everything just looks like typical Bayes. We haven't done anything weird or fancy. I've just said I'm going to commonly push all of the theta i's towards a common parameter. Now that is inducing bias. So we're biasing our estimates by doing this. Maybe that's a good thing. So what you can do by building regularization into your problem, i.e. shrinking, i.e. building a prior that's common to every parameter, is I can reduce the variance in the space. So I can bring down my variability in how well I do in a scoring function like this on average. So while I might have bias, it turns out I'm going to overcome that with a reduction in variance. And you can think about it like this. I'm pushing everything in a common direction, and so I've got traction between all of my estimators for each one of the theta i's. So, and that reduces variance. Question is does it reduce variance enough to overcome the bias that we just brought into everything? And James and Stein told us, yes, it does do this. And so Bayesians are oftentimes, if they shrink, giving you slightly biased answers, but they're giving you a trade-off. And that's reducing the stochasticity in your estimators. How well is this estimator working? Is it moving all over the place? Or is it kind of stable? Okay, so that's the concept of variance. And both of those things are how we need to think about how well our estimators are working. Both the bias characteristics and the variance characteristics. So if we're wrong, and we always will be wrong, it's either because we're wrong systematically or because our answers vary too much. It's one of those two things. Okay, so just for those of you that have taken inference or have taken a decision theory class, this assumes an L2 loss function. L2 loss. Or quadratic loss. Okay, so when we work with Gaussian stuff, this is very typical because if we think about the Gaussian function, we've got that squaring function in the exponent. And so it's a fairly natural norm to work in when evaluating yourself. Of course, if I had data that was coming from a Laplace distribution or something like that, the L2 loss function wouldn't make a lot of sense to me. So I'd probably move to the absolute loss function. So lots of discussion there. We're not going to have it in this class. Okay, so what does a Bayesian do? Once they get this, they multiply their prior times their posterior, or their prior times their likelihood, and they induce their posterior, and they go to town. Of course, you have to select the hyperparameters, so we're going to have to pick these. So how do we choose? So we're going to be biasing everything, so we better be careful in how we do this. So Empirical Base gives us a method for doing this. So step one, find the marginal distribution. I'll point out that the typical answer for the Bayesian is going to be the expected value. So the expected value of this posterior distribution is just this. I worked it out for you. I wrote it down a little bit differently than we wrote it in the first couple weeks of class. I had everything kind of written down in terms of precision, so if you change all of these onto their precision scale, that's how we wrote down the analysis. Of course, I can flip everything back to variances, and this is the expected value of the posterior distribution you get from the likelihood coming from this, using that data, and this prior. So the expected value for each one of, this is going to be for the theta i's, right here. So my apologies. So theta i's. So the posterior has the expectation of the posterior. This, of course, is going to have the xi in it. It appears right here. And so our answers are still kind of independent of each other. And so all these xi's just appear one place in this equation. So here's the twist on everything. And so we're going to marginalize everything. So that's step one of our empirical Bayesian method. In the marginal distribution, it's just this. So I'm marginalizing over my theta I. I'm getting rid of the thetas. It turns out it's normal with mean mu. Where else would it be centered? And variance this. You could do this integral by hand. You could use the iterated expectation formulas. So something like this. Expectation. I'll leave it to you to just walk through it, but it's mu. I don't want to go through it all. We've done this in class at least 2 or 3 times. But just use your iterated expectation to figure this thing out. We'll do it. Xi given theta I expectation. This is expectation of theta I. So expectation of xi given theta I, its mean is theta I. Expectation of theta I, that's our prior distribution right there. This is mu. We can do the same thing using the iterated variance formula, and we get sigma squared plus tau squared.
Notation was that theta I shouldn't be there. F of xi conditional theta I, but you're integrating out theta I.
Theta I is getting integrated out. So I'm going to leave this here.
Okay.
So this is the expectation. Oh, you don't want this theta I.
Yeah.
Got it. Sierra's right again. She wanted me to remove this. So the calculation is correct. I don't have the theta I. This is what's being integrated out. So yeah, good call. So no theta i's in there because we integrated them out. Yeah, that would have been massively confusing without that. So thanks again to Sierra keeping us on track. So this is my marginal distribution. And the question is what are we going to do with this thing? So this depends on the hyperparameters. So this has the mu in here. So it has mu and it has tau. And you can see it in the equation. We've got mu there and we've got tau. And so step 2 is to maybe do something with this. What we could do is we could maybe maximize this distribution over xi. So we could maximize this. We had alluded to doing that. I'm going to do a method of moments technique, and I'm going to do it fairly arbitrarily, although this one is typical, this estimator that comes up. The paper that I'm going to send out to you, written by George Casella on this, which is fantastic, he presents this example. And so some of this is done for simplicity's sake. But this part's easy. So I happen to know, so x bar, I'm going to now coalesce all my data and think about it together. So this is just sum of the xi's. I goes from 1 to p. So I know what this is. So this is normal for all of the xi's, so they all have mean mu, and when I average over them, I don't change anything. That has mean mu. This doesn't feel very arbitrary. So what we're going to do in the method of moments technique, so this is method of moments, mom estimators. This always seems to crack people up, it still cracks me up. So the mom of estimators. This is a little bit unfortunate if you have a good mom, because this isn't always the best estimation technique. I think in this case it works out okay though. So go home to your mothers and apologize that they didn't get a fair shake. They should get like the MLE or the posterior map or something like that. So here's how the mom estimation works, is I'm going to take now mu hat and I'm going to set it equal to x bar. So I take that and I set it equal to this. And so I'm going to call that mu hat mom. Now this one feels a little bit more arbitrary. I'll write that big over here. Give myself a little bit more room. But we're almost done with the hard part. Now again, these are choices that we make. We would probably want to make a couple choices, figure out different ways to fix these parameters and see if maybe you can get an answer that's more desirable to you. So that's why I have my piece of paper, because I don't remember this off the top of my head. But it turns out expectation of p minus 3. So there's that 3 that I was talking about, over sum of the xi's minus x bar squared. So I'm coalescing my data again, I'm bringing it together to build an estimator. We can figure out what the answer to this thing is. It turns out this, p minus 3, I can pull the sigma squared out. And George Casella doesn't motivate this very well in his paper. It's just a choice that he makes and then he moves on. There's other ways to do this. Expectation of 1 over sum of the xi's minus x bar squared. Okay, so this is some random variable. And we can figure out the answer to this. Let me just ask Sierra, since she's on the ball today. What distribution does this thing follow? Usually I pester you guys with this, and I haven't done this yet. Okay, let me ask the question, what distribution does this follow?
So variance is going to be a scaled chi-squared.
It's going to be a scaled chi-squared. Yeah, so this is an inverse chi-squared. Boom.
Get that.
She got it. So this turns out to be inverse chi-squared. So normal squared or chi-squared, it's going to have some scaling parameter to it. Because they're variance sigma squared in all of this. But the whole thing right here is an inverse chi-squared distribution. If you didn't know that, that's okay. But it turns out this expectation, if you went to an inverse chi-squared Wikipedia table, you'd be able to figure out what the distribution of this thing is, and you'd work out its variance. It turns out the answer to this part is 1 over p minus 3 sigma squared plus tau squared. So that's why they presented the p minus 3 up top here, is it ends up canceling this other one. Okay, so this whole thing is going to be sigma squared over sigma squared plus tau squared. So it's not completely arbitrary why George Casella did this. This is a very simple form right here. So here's the method of moments step. I'm going to match this moment. So they don't actually have to be moments per se. In the traditional sense, it's just going to be some function of everything. So I take an expectation over something. So lots of ways to do method of moments, an infinite number of ways. But that means our mom estimator for this And when I do this, I need to be putting a tau on everything. And so what are we estimating? We're estimating tau. That's our variance in our prior. We already have a good estimate, maybe, for mu, and it's probably what you would have been inclined to plug in the first place. So I don't like when I see people do this and get willy-nilly about what their variance is. Because if they're not calibrating that variance right, they're putting too much mass and too much certainty on x bar being the answer. And so they're going to co-estimate the variance. So here's what we do. I take sigma squared over sigma squared plus tau hat squared. So I put this hat on here to show you this is an estimator now. And I'll write mom, if you will. Some people might say it's the Empirical Base estimator, and maybe that's the right way to think about it. So this is going to be equal to p minus 3 sigma squared over my sums of squares. Okay, so while it's true that the expectation of this quantity is equal to that, it's not true that the thing inside this thing is equal to that. On average, this is true. So this is really an approximation, but as soon as I set it equal to each other, I have to say that's not tau anymore, that's just our estimator. And what we can do is I can solve for tau. So, and I won't go through the algebra of doing that. We're all capable. But I'll write it down. This is going to be sum of the xi's minus x bar squared divided by p minus 3. Turns out there's forms that you can get of this that have a p minus 2 in there. And so you'll notice that if this thing is negative, this answer probably doesn't make much sense. If p were equal to 3 right here, this isn't going to work. So I would only recommend this answer if p were 4 or greater. There are Stein estimators that have a p minus 2 in there. And so you can use this analysis when p is greater than 2, i.e. it's 3 or greater. This analysis is a little bit weaker, so I think that there are better Stein estimators that exist. So this is that thing minus sigma squared. Once you solve all of this. And remember what we came up with, mu hat mom is equal to x bar. So these are our empirical Bayes hyperparameters. So what we did is we marginalized and then we did a funny non-Bayesian thing to come up with these hyperparameters. You can't really do a Bayesian analysis on it because you're leading yourself right back into the exact same problem. What are your hyperparameters on your hyperparameters? So what we do with everything is we go back and we plug everything back into this answer. So we go back to our posterior estimator. And we plug everything in. So at the end of the day, this is the estimator that the empirical Bayesian might be using. Of course, there's other choices. So our estimator for theta I in the first place and I'll call it the James-Stein Estimator because I'm going to plug these things in. So this is called the James-Stein procedure for doing this, shrinkage techniques. This is just going to be what we did before, sigma squared over sigma squared plus, I've got tau in there, so I'm going to replace tau with this whole thing. So I'll just write it down. Just remind you what we've done. But this is going to be this whole quantity right here. Then I'm going to have mu hat. Mom plus tau hat so again this thing right down here, mu hat mom, that's just x bar. Same thing gets plugged in there, times xi. So that's our data right there. So for estimating theta I, I've constructed another estimator, or MLE just uses, when they estimate theta I, just xi. The James-Stein approach, the shrinkage approach, the things that maybe Bayesians do, is not just xi, but it's a weighted average of xi and x bar. And so we're using more data points. We're using all the other data points to estimate theta I. And originally everything was independent of each other. This was an incredibly surprising thing to come up with back in the day, and people thought, this is nonsense. This doesn't make any sense. Why would you ever do this? This is a pretty good answer in some sense. When you're trying to understand what the total risk is in your system, i.e. MSE, this answer is better than this answer. I'm going to give you another James-Stein estimator as well. We could have made this simpler. If you don't like this answer, I can understand. But let's say I did something like this. Let's just say that I just picked this thing right here to be 0. So if I just fixed it to be 0 and it's not a parameter that I need to play around with, I wouldn't have had this part come into everything. Everything else would have turned out the same though. And so if we chose mu equal to 0 in the first place, i.e. theta I is coming from a normal, it's 0, and it's got some variance in here. What we'd be doing is we'd be shrinking all of our estimates towards 0. So let me just write that down. Shrinkage towards 0. Okay, so I'm going to shrink it in a particular direction. This estimator shrinks everything ultimately towards x bar, the mean. And so on average, you tend out being okay because of this. This is also going to be a good answer as well. But the James-Stein estimator that we're going to get, E theta hat, and I'll call this James-Stein 0. I'm going to compare these answers. I want you to see what's going on with this solution. And that's why I've opted to pick the 0 point to shrink to. So this is going to be expected value theta I. This is theta I hat. I'll call it James-Stein 0. This is just going to be this part of the equation. So this is going to be some sort of weird scaling of xi. So tau over sigma squared plus tau squared. Let's throw my hats on there. This function that I wrote down previously times xi. I probably should not have erased what tau was, so I'll just rewrite this in, and I'll write out the whole full-blown glory of this. So this is going to look like, we'll say, sigma squared, and I'll just write this in. Sum of the xi's minus x bar squared divided by p minus 3 minus sigma squared. So this is going to be plus sum of the xi's minus x bar over p minus 3 minus sigma squared. So we see some cancellation here. So it's kind of a funny answer that we end up getting. So you can rewrite this however you want, but we can kind of see all of the data is coming in to estimating the theta i's, and you might think that's really strange. Now, working out the mean squared error for everything would be a little bit difficult. So what we need to do, so our mean squared error is this integral. So I'll say, at least theoretically, this is what it would converge to if we did this over and over and over again and we simulated it. What we'd be looking at is our estimator, E for theta I, minus theta I squared, where my x's are going to be generated. So this is a function of x. If I were using the MLE, I'd plug xi right in right there. If I were using the James-Stein Estimator, I'd plug that thing in right here. And I would try to integrate this over all of my data. So this is going to be cap x given theta I sigma squared. And I'm going to integrate out x in all of this. So this is an average over data sets right here, and I'm going to be comparing my estimator to theta I in the squared error sense. So this is MSE for us. So what you could do is you could build a simulation where you sample data out of this, plug in your estimator, and then turn this into a big sum. So let me just write that down. This is a hard integral to work with in general. Turns out for the MLE, you can work this out in closed form solution, and it's going to be the dimension times sigma squared. We'll look at that in a second. For the James-Stein Estimator, I've got the xi's coming in the numerator and the denominator of this function, and it causes a mess. In that integral, I don't know how to solve analytically. I don't know if anybody does. So, might be possible. But what I can do to evaluate this integral is I can treat this like a sum. I goes from 1 to, I'll say, n replicates. So I'll say, let's do R for replicates. This is going to be e to the theta I, so a function of the data minus true theta I squared where the data, and I'll divide this by R, where each one of my data points, my data, I'll say, for the rth replicate is coming from fx given theta. So I'm going to sample data points. Let's make this the rth replicate. From my original function, this thing. So I sample data from this. I do it p times. I get that data. I plug in my estimator that I compute from my data. I compare it to the truth. I square it out, and I average. This, as R gets really big, will converge to this integral. That's called Monte Carlo. So I've built a Monte Carlo method for comparing the MLE to the James-Stein Estimator. So let me just write that down, and we'll conclude after I show you the results. So let's compare James-Stein to the MLE. And quite literally, this is a result that shocked the world. Shocked me too when I first saw it. Even though people were telling me that it was true, that the MSE for this estimator could possibly beat the MLE. I didn't think it was possible. I thought that they were confused, and I think I was thinking exactly like a lot of other people when they first saw this analysis, because it's confusing. Again, what's happening here is the shrinkage towards a common parameter is pulling everything down. So let me just show you real quickly. I did this for 10 dimensions. So for this analysis, I picked P was equal to 10. Now I need to pick P greater than 4 for the analysis that I'm using. Here's the actual risk. So I think anybody that's taken an inference class or a couple probability classes could work out this integral for the MLE. So the red is the MLE, right here. And it turns out it's 10 times the standard deviation. So the MSE for the MLE, is going to be equal to P times sigma squared. You can work that out. Really, you're looking at a variance of something. You're looking at that squared error expectation. I picked this to be 1, and I picked this to be 10. And so that's the red line. That's what it theoretically is. But I don't know how to do the integration for the James-Stein Estimator. And so I do know something, though. I know Monte Carlo, and I know how to approximate it. So anytime I get stuck on doing my math, I pull out my computer, and I brute force the thing. What I'm showing you with this picture is that I can construct a Monte Carlo estimate of this straight line. Now, I didn't do a lot of replications in here, and I have some degree of variability in estimating this straight line. And you might say that is not a very good approximation of the straight line. But I want you to look at the bounds right here. It is pretty close to 10. And so what I did is for differing values of theta, so the bottom axis is theta here. So this is a function of theta. This is MSE. Sometimes we call that the risk function under the L2 loss, which is the natural norm for the Gaussian problem. It's probably what I would use, depending on what I was doing, of course. And I'm pretending I don't know how to solve the integral, and I have some approximation. If I crank up cap R in my Monte Carlo simulation, this will get tighter and tighter and tighter around this. So for differing values of theta, I ended up doing that integration. Okay, that doesn't help us too much. This is that same picture. So when I put it on a different scale, That blue line looks like it's a pretty good approximator of the red line. And so that's about how good my computationally approximated Monte Carlo simulation of the James-Stein risk is. And so I did the exact same thing for that James-Stein estimator that we just computed. Keep in mind that I shrunk everything towards 0. So I made a specific choice. And so that biases the Bayesian towards 0. So if true theta, again, this is the x-axis is theta here. So it's true theta, and I use common thetas for all of mine. My 10 things, I use the same theta. That's why I'm able to plot this in one dimension for us. So if true theta was 0, I take that back. I generated my thetas from my prior distribution in the first place. So I have a random generation of it, and this is the norm on theta. So that's just the norm, and I probably should have written that down. That's the norm of theta, and it gives us a one-dimensional way of looking at this. Remember, this is a function of many thetas. So this is the norm over those thetas, and I generated the thetas randomly. So I generated the thetas randomly, and then I generated the data randomly. And then I plotted everything in one dimension using a norm on theta. So again, this is 10 times 1, which is the risk function for the MLE. The Bayesian is obviously going to do better if theta is 0. If true theta was 0, the Bayesian does better over here because they've shrunk the analysis towards 0. No surprise. So if you happen to think theta is in a particular range, I can regularize and shrink towards that. And if true theta is over there, I'm going to beat your technique, probably. So, no surprise. It goes up as we move away from theta. Here's the surprising bit, is this line never goes above the MSE for the MLE. It's a mouthful. So, it asymptotes into it. So as theta gets really, really big, the James-Stein method ends up very competitive with the MLE, and it's a whisker that it beats it at. But this result kind of shocked the world, and what I want us to take home by looking at it is that this has one of our favorite components of Bayes built into everything. It's got shrinkage. So when I'm self-regularizing the space, I was checking on the camera there and freaking me out that I have to do the whole lecture all over again. So that would be Murphy's Law, of course, but we are right at the end. And so if you have knowledge of where to shrink to, go ahead and do that and you'll do well in those regions. But also if you're trying to do a joint estimation of a lot of parameters, and it is in a network sense, that you're going to score yourself in a global sense on how well you do on average across all of your estimations, shrinkage is a very good idea. What we're doing is we're building some bias into our analysis, and we're winning by reducing the variability in everything. And so, and we've seen that. So in our beta binomial problem that we confronted in the beginning of class, we regularized and penalized the sides. Our estimators, the MLE, over on the side of that space 0 to 1, for the beta binomial example, when you're estimating P, the probability of the binomial, over in the ends, the MLE doesn't perform very well. In regularizing that helps us to estimate things over there. We're building a little bit of bias in, but we get a huge benefit. And it impacts everything that we do, not just our estimators, but also our coverage rates. And so we studied that and we learned that early on. So what I want to conclude with is that Bayes has a regularizer in there. If you're not a Bayesian, go ahead and regularize anyway and call it something else. So you could call it regularized likelihood functions. And there are people that walk around and say, well, I'm a likelihoodist, but I like to regularize. And usually I think that's a Bayesian. So, but maybe they don't like to think about it that way, and that's okay. But regularization is a good thing if you regularize reasonably. The other good thing about Bayes is the joint estimation of all parameters. And so we are able to co-estimate all the parameters and understand their associations. So when we go back to the joint normal analysis that we studied, we built some MCMC for it, we noticed that our estimate of phi and our estimate of mu had something to do with each other. So if phi changed, then our bounds on mu also changed. And so you want to think about estimators together if they're coming from the same process. So the other thing you could do if you weren't a Bayesian is you could look at something like S squared, your typical estimator of variance, and X bar. And the classical result is that those two things are independent of each other, and they are. But if you look at the likelihood function, mu and phi can't ever be factorized away from each other. So they should be co-estimated. And building independent estimators isn't always what you want to do. So Bayes does two really important things. Regularizes and joint estimates. This is kind of just a neat result. You can think about it. We'll post notes if you want to go and review over this. But this is what people are talking about when they say shrinkage estimation. Another thing that they're saying is we're being Bayesians. At least that's the way that I understand it. And probably the part that you guys found most compelling is all the MCMC stuff, all the computation. That we're working in a probability space, we've put our inference on that, and so what we need to do, if we can't write down the distribution and understand it analytically, is we can sample from that distribution. And if you can sample from a distribution, then you can estimate anything you want. You can estimate your intervals. I had you do that via Monte Carlo in a simulation. It took a lot of time. If you use the quantile function to estimate your intervals, it was much faster. And so that's kind of a take-home point that if there's something you can do analytically inside your computation, you should do it because it'll speed up your code quite a lot. It'll drive down the stochasticity. For give samplers, it'll make them converge faster. And so there's lots of stuff to think about. But really, in a nutshell, it's all about what properties you want out of your posterior, and that's going to make you choose different priors that are going to regularize your space in slightly different ways. If you have a lot of data, then it doesn't matter. The likelihood takes over and the impact of the prior starts to wear off. That's all true. So Bayes is kind of a funny thing. You know, there is a lot of math involved, and there's a lot of calculations involved, and there's a lot of integrations, and I think that's what scared people off back in the 60s, is we can't do the integrals. Can't figure out the denominators, we don't know what these distributions are. You know, if I'm trying to figure out joint variances of everything, I've got a difficult integral to work with. Nowadays we have MCMC, so in the 90s, that changed everything. And so instead of Bayes being a hard math problem, it was a manageable computational problem. So take that all to heart, and hopefully I see you around campus next semester. And if everything is opened up in the fall, swing by, say hi, I always enjoy that. But you guys have been a pleasure, so thank you for making this semester successful. That's it.